I want you to be mine again, baby.
Sup, guys? This is Physics 2212 Lab 6 Magnetic Molasses. My name is Ben Hovey. If you are actually listening, comment about the intro music. I want to hear it. Okay, guys, the purpose of this lab is to compare the experimental time it takes for a bar magnet to fall through a tube of aluminum foil with a simulated time calculated by a computational model. Some assumptions we got. The system is the bar magnet. The surroundings are the roll of aluminum foil, the earth, and everything else. We got negligible air resistance in the computational model. The induced magnetic field is what is affecting the magnet's motion. The aluminum foil is uniformly distributed. The length of the tube is 0.28 meters. The width of the foil is 0.006 meters. Inner radius is 0.022 meters. And the outer radius is there because I don't want to say it. And the mass of magnet is right there. Magnetic dipole moment from lab 4. Kaboom! The results are as such. The average experimental time was 1.42 seconds, and very close, the predicted time was 1.465 seconds. That was pretty dang good. Fundamental principles. We got Faraday's law, the magnetic field of a dipole, position and velocity update formulas, magnetic force on a wire loop, electromagnetic forces, and the force of gravity. All these formulas play pivotal in our code, which is going to be up soon. Experimental procedure. We're going to start our recording, okay? We're going to drop the bar magnet through the tube of aluminum foil as you see here. Repeat that 5 times to get an average. Watch through the video to find timestamps for every magnet entry and exit. Calculate the average time spent by the magnet inside of the tube. Here's a little video for your pleasure.
All right, 3, 2, 1.
Wow, look at that. Pretty dang cool. Computational model time. We have our constant right there. We put in the lengths. We put in all this stuff. There's a lot of code here, so I'm not going to go through all of it. Of course, there's screenshots of some of the most important stuff. If you want to sift through it all, check out the link in the bio, okay? But here is some code. You can look at it if you'd love to. I hope you do spend a lot of time on it, okay? Here is all the other stuff. Since we don't have a lot of time, I'm going to move on to the next step. But if you'd like to go through the code, by all means, do so. I'd love for you to do that, okay? Observations. The intensity of the color on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current as viewed from above, and which counterclockwise? How can you know? So, as this is kind of how we're going to interpret our GlowScript data, our GlowScript computational model, okay? Applying Lenz's law, the red color must be counterclockwise and the blue clockwise, as this combination would oppose the magnet's motion. What happens to the dynamic of the system when you flip the magnet around? The dynamics of the system are not changed. The magnet would still slow down, but the currents would be the opposite in this experiment. How does the total time in tube of your real-world system compare to that of your computational model? How might the computational system be made more accurate? The computational system does not account for external magnetic fields or forces like air resistance and friction. What does the shape of the velocity versus time plot right here tell you about the forces acting on the magnet? The forces are unbalanced for this first 0.1 seconds, right? And then over 1.3 seconds-ish, they balance out and they equal each other. But for those last 0.1 seconds, once again, they're not balanced. And this is simply because due to that entry and exit of the magnet, it has the magnetic field or the force of that aluminum roll is not as strong at those points. Sources of error. So some sources of error as such. Other magnetic fields were definitely present. We had magnets flying around left and right, and we had people playing with magnets. Probably could add a little bit of error in our experimental model, or experimentation. Errors when measuring visually. So that's when we were like checking out the timestamps. We definitely made a lot of errors. We were kind of just rough sketching out when it entered and exited, and that could have easily added some error. Friction with the walls of the aluminum roll. Of course, the magnet is touching the aluminum roll walls, and so there's definitely some slight friction going on there, which would add another force that we didn't account for in the computational model. Air resistance is not accounted for in the computational model, but that's definitely present as we have the air resistance of our natural world. The non-uniform distribution of the aluminum foil. The aluminum foil wasn't perfectly distributed around the cardboard tube. So that means that at some moments there was probably stronger or weaker magnetic forces. What if the resistivity of the conductor were reduced as close as possible to zero? And nearly zero resistivity would imply a very small resistance and thus a very large current. This would increase the magnetic force and make the magnet fall very slowly through the tube. What if holes or slots were cut into the tube? Holes or slots cut into the tube would disrupt the induced current and decrease it, reducing the magnetic force on the magnet and letting it fall quicker through the tube. Thank you guys. I hope you enjoyed. Thanks for the last Physics 2 lab. I will see you next year if you're doing mechanical engineering. Hey, I